Okay, let's start off by going through the assignment. So describe the trend of the world's energy use from 1850 to present, and that would be exponential. That's it. So exponential would be it. Define per capita, so that's per person. List 3 factors that affect energy use. So your population, your climate, and the type of things that you manufacture, right? So like oil is going to require a lot more energy than tourism. What are some ways that populations can decrease their energy use? So decrease their energy use would be using more energy efficient things like light bulbs and vehicles, and all of that would help decrease their energy use. That would be the number one way to do that. Okay. So let's do these sample diploma questions. Make sure you try them on your own. So during the past 100 years, global energy consumption could be best described as the following growth rate that is exponential. So it's going to be exponential. And in comparison to other industrial nations, Canada per capita energy consumption is higher. 2, the highest energy use per capita tends to be in areas of the world that are, so it's talking about per capita, so highly populated wouldn't be the answer. Large geographical area does not matter, and have warm temperatures would be colder temperatures, so heavily industrialized, so the type of industry that you have, if it's heavily industrialized, it's going to use more energy per person. And then this one, a power plant provides an input of 450 megawatts to transmission lines. If the long distance transmission line is 92% efficient, then the power output after the transmission would be, so we're trying to find output. So our formula is out over in times 100%, and the 100% is on top. And that equals our efficiency. So we want to find the output. So we move the input up top, and then we move the 100% down below, and we can plug all that in to our calculator. So our efficiency is 92% efficient. Our input is 450, and then we divide it by 100. So it's going to be 414 as our answer. And then this last one is a little bit tricky. Ranked in order from the region that uses the least amount of energy per capita to the most. So it's kind of weird because these are in percentages. But if you think of it per like 1,000 people instead of per percentages per 1,000, right? So this would be 229 per 1,000. This would be 239 per 1,000 joules or watts or whatever. This would be 340, and this would be 64 per 1,000, right? If you add this all up, it'll make 1,000. If this is per 1,000 people, this has 51 people, this has 112 people, this has 560 people, and this has 68 people. Okay, so all we have to do to find per capita always is we just have to divide the energy we use per the number of people, right? And it's the same numbers. So 229 divided by 51 equals that. And even if I use the original numbers, I just use 1,000 because you can't have, if I used 100, it would be 5.1 people, which would be weird. But if I go 22.9 divided by 5.1, right? I just plug in those numbers as is. It's the same answer, right? So 229, and they have 51 people. That's what I get. I have 239, and then I have 112 people. That's what I get. I have 340, and I have 560 people. That's what I get. And then I have 64, and I have 68 people. And that's what I get. So we can see the order. So we want to do from least to most. So this one's the least, and then this, and then this, and then this. So that's what I'm going to put. So it's going to be 3, 4, 2, 1 as my answer. Just take your energy in whatever form it is, divide it by the number of people, And that's how you have per capita, and that's how you can rank them per capita. Okay, so today we're going to be talking a little bit more about fossil fuels. Are we running out of fossil fuels? Because there are too many naughty kids. I didn't get this right away, but it's because they get coal, so that's why we're running out of fossil fuels, because Santa's giving away all the coal. Curriculum. They explain the need to develop technologies that use renewable and non-renewable energy sources to meet the increasing global demand. Describe various impact of developing and using various energy sources, so conventional oil sands, coal burning power, and describe how Aboriginal perspective of an interconnected environment demonstrates the need to balance resource extraction with environmental impact. So, where does almost all the energy on the Earth come from? The sun. In what form does this come to the Earth? So it comes as EMR, or light energy. And when plants undergo photosynthesis, what form is this energy stored as? So when plants undergo photosynthesis, they take carbon dioxide, and they take water, and they turn it into glucose and oxygen. So this glucose is where it's stored, and this is just sugar. So anytime you have sugar, it's going to be stored as chemical potential energy. Okay, so it's stored as chemical potential energy. So where do fossil fuels come from? Well, fossil fuels come from plants. They come from fossilized plants, right? And plants they store it as chemical potential energy. That's what we're using when we're burning fossil fuels, but the original source of energy from those plants is light. Right? Lots of people say that fossil fuels come from dinosaurs, but it doesn't. Fossil fuels are much older than dinosaurs. We'll see that in a video. Dinosaurs were like 65 million years ago, and then these are like 300 million years ago, so much longer. So fossil fuels come from fossilized plants. Plants store it as chemical potential energy, but plants got their original source of energy from the sun, and that's important. Okay? Fossil fuels come from the sun. So how are fossil fuels formed? So let's watch this video.
Fossil fuels. Fossil fuel is a term used to describe a group of energy sources that were formed from ancient plants and organisms during the Carboniferous period, approximately 360 to 286 million years ago, even before the age of dinosaurs. At that time, the land was covered with swamps filled with organisms and plants. As they died, they sank to the bottom of swamps and oceans, and over millions of years started decomposing under layers of sand, clay, and other minerals. Different types of fossil fuels formed depending on the combination of organic matter, temperature, time, and pressure conditions while decomposing. There are three major types of fossil fuels: coal, oil, and natural gas. Coal was formed from ferns, plants, and trees, which hardened due to pressure and heat. Oil was formed from small organisms like zooplankton and algae, where pressure caused the more complex organic matter to decompose. Natural gas was formed by the same process as oil, only it was exposed to more heat and pressure, causing it to further decompose and turn into a gaseous form. Fossil fuels are sought-after energy sources because they have a high energy density. They are the world's dominant energy source. Fossil fuels have a variety of applications, from electricity production to transport fuels. They can also be used to make a variety of common products, from plastics to cosmetics to even some medicines. These resources have powered industrialization over history and continue to do so today. Fossil fuels can be an abundant and cheap, or in some cases, a scarce and expensive form of energy, depending on geographic location. For this reason, geopolitical issues arise due to scarcity caused by the natural geographic allocation of these highly valuable resources. Fossil fuels are considered non-renewable resources because they take millions of years to form, which means that once they are used, the resources will not be replenished in a human lifetime. The gradual depletion of the most accessible fossil fuel reserves have forced companies to develop technologies for extracting more challenging or unconventional reserves. In many cases, this means additional safety and environmental concerns as well as higher costs. Fossil fuels are also the largest emitters of carbon dioxide, a greenhouse gas which causes climate change. In addition, their production causes both environmental and human health issues. These concerns have triggered society to look at alternate sources of energy that are more environmentally sustainable and renewable. That's fossil fuels.
In developing countries, their main source of fuel is wood, which is gets its energy source from the sun. It's just not as old. So collecting wood is very time consuming and exhausting. And then this is a picture here of what developing countries would use to cook their food. It's just an open fire pit like that. And when wood is burned, it's releases carbon monoxide, particulate matter, other pollutants. So it's not super good to breathe in all the time. You know how it can be breathing in smoke. What developed countries found is that coal is a cleaner burning fuel, but still releases a lot of particulate matter and SO2. So coal is better than wood, but it is really bad for particulate matter and SO2. And particulate matter is it just releases particles into the air, and SO2, we learned before, leads to acid rain. Okay. Coal also contributes to the thing called thermal pollution, which is hot water. And I'll show you how a coal power plant works in the upcoming lessons. On the next slide, I'll show you how a coal power plant works. You need hot water for it, and I'll talk about that on the next slide. So this is traditional renewable fuel, so that would be things like wood. So you can see around 1880s, it's gone down, and then with that was a rise of coal. But because coal is bad for the environment, particulate matter, SO2, it's really, really bad for that. You can see that coal has decreased over the last 40 years, 50 years. Okay, so this is how a coal power plant works. So this is the coal supply. It goes in here, they crush it up, and then it goes into the boiler. So when they put it in the boiler, they just heat it up and it starts to burn. So you have a fire here that's powered by the coal. And then here you have water. So what you're looking to do is you're looking to heat up that water, shoot it through this pipe, and it's hot steam, so it shoots through really fast. It turns this generator, which we learned in the last unit how to create electricity. You just need to move a coil by a magnet or a magnet by a coil, either one, but this will generate electricity and then it can go out to people. So you need to know the energy conversions that happen with a coal power plant. So this coal right here starts off as chemical potential energy. So that's where the energy is stored in the coal, is chemical potential energy. Okay? And then heat is a type of energy, so it turns into heat over here, and it heats up the water. And then once the water is moving water, anything moving is kinetic energy. Okay, so the chemical potential turns into heat, turns into kinetic energy, and then after it goes through the turbine, it turns into electrical. And we can use it for light, we can use it for kinetic, we can use it for anything that we want after that. So you need to know these energy conversions for a coal power plant. So coal lies beneath the surface of the earth, and large mechanical shovels and trucks are used to move it. So you just mine it and you just dig up land and you find the coal in there. It's relatively inexpensive to mine, and that's why it's so popular, is because it's cheap and people like cheap energy sources. So after the land has been mined, it goes through a process called reclamation, and that's where the companies need to restore the land to what it looked like prior to the mining. So that's really important. You can't just leave these open pits. You have to bring it back to how it was. Okay, so that was coal, one type of energy source, and the video talked about how coal was made. So the other one is type of petroleum. The other type is petroleum. So petroleum is liquid hydrocarbons. And you can see as coal went down, petroleum went up, and natural gas went up to replace them. So petroleum, so like car gasoline would be petroleum, oil would be petroleum, kerosene from a kerosene lamp would be petroleum. All those would be classified as petroleum. So to extract oil or petroleum from the ground, you use the enhanced oil recovery process, and that's where water, chemicals, gases are pumped into rock layers and force the oil into a well for extraction. So here's a picture of it. So this is the chemicals and the steam here. So what they do is they send the chemicals and steam down here, and it helps push all the oil that's in the ground over here, and then the oil gets pumped up through here, and then they collect it. And this is called a grasshopper that pumps the oil out of the water. So what advantages and disadvantages of extracting this way, oil this way compared to coal? Well, with coal, you need to extract this whole area of land. This is tiny. You could have this on farmland. So an advantage, so we'll put advantages over here and disadvantages over here. So an advantage to doing it this way is less land use. Okay, so that's good. A disadvantage is you're pumping chemicals in ground, and that's not good. You don't want to pump chemicals into the ground. If this mixes with the drinking water, it can have dangerous effects for people. Other advantages to this would be once you set it up, it's good to go, so you don't need a lot of man labor to, or woman labor, to extract it after this. Once you set it up, you're good. So once you set up, you're good. And the disadvantage is it would be a little bit more expensive to set this up. Right, but once you set up, you're good. So yeah, there's advantages and disadvantages to both. So oil sands oil is petroleum, so it's another type of extraction process. So Alberta's Athabasca region contains oil, but is trapped in sand and makes it difficult and expensive to extract. So the problem is that you have this oil sand mixture that you have to dig out. You have to wash it with solvents to extract the oil from it. So when they wash it with solvents, think soap as a solvent, like soap, sort of break things up. This creates a product called bitumen, which is black tar. So this is what they want. And then tailings is the leftover waste. So this has the solvents in it and the sand in it as well. So this is a tailings pond, and this is all the waste. And what they need to do is they need to let this settle into layers like oil and water, and then they collect it. But these are really, really dangerous, and what happens is birds can fly in. So these are birds flying in, and if they land in the tailings ponds, they die, and that's not good for the environment, that's not good for the birds, that's not good for the ecosystem. So these tailing ponds are really toxic, and they need to leave them for a while before they can clean them up. So definite disadvantage to oil sands there. So the last type of fossil fuels is gas. So natural gas is the most common one. So natural gas is a mixture of small hydrocarbons. So it's mostly methane. So CH4 is methane, and you need to know that that is the main source of natural gas. So mostly methane. Oh, I have it written there, with a little ethane, propane, and butane, but it's mostly methane. So natural gas is extracted by deep drilling, and it's kind of similar. They shoot chemicals and water underneath here, and then they collect the methane gas. But I have a video that shows this a little bit better. And collecting natural gas is the process fracking. So this is a video that talks about fracking.
Deep underground lie stores of once inaccessible natural gas. This gas was likely formed over millions of years as layers of decaying organisms were exposed to intense heat and pressure under the Earth's crust. There's a technology called hydraulic fracturing, or fracking, that can extract this natural gas, potentially powering us for decades to come. So how does fracking work, and why is it a source of such heated controversy? A fracking site can be anywhere with natural gas, from a remote desert to several hundred feet from your backyard. It starts out with a long vertical hole, known as a wellbore, drilled down through layers of sediment. When the well reaches 2,500 to 3,000 meters, it's at its kickoff point, where it can begin the process of horizontal drilling. It turns 90 degrees and extends horizontally for about 1.5 kilometers through a compressed black layer called the shale rock formation. A specialized perforating gun is then lowered and fired, creating a series of small inch-long holes that burst through the well's casing into the rock layer. About 3 to 4 months after the initial drilling, the well is ready for fracking to begin. Fracking fluid is pumped down into the well at a pressure so high it cracks the shale rock, creating fractures through which the trapped gas and oil can escape. The fluid itself is more than 90% water. The rest is made up of concentrated chemical additives. These vary depending on the specific characteristics of the fracking site, but usually fall into 3 categories. Acids for clearing debris and dissolving minerals, friction-reducing compounds to create a slippery form of water known as slick water, and disinfectant to prevent bacteria growth. Sand or clay is also mixed into the water to prop open the fissures so the gas and oil can keep leaking out, even after the pressure is released. It's estimated that all of fracking's intense pumping and flushing uses an average of 3 to 6 million gallons of water per well. That's actually not a lot compared to agriculture, power plants, or even golf course maintenance, but it can have a notable impact on local water supply. And disposing of used fracking water is also an issue. Along with the trapped gas that's pumped up to the surface, millions of gallons of flowback liquid come gushing up. This liquid, containing contaminants like radioactive material, salts, heavy metals, and hydrocarbons, needs to be stored and disposed of. That's usually done in pits on site, in deep wells, or off-site at water treatment facilities. Another option is to recycle the flowback liquid, but the recycling process can actually increase levels of contamination since the water is more toxic with each use. Wells are typically encased in steel and cement to prevent contaminants from leaking into groundwater. But any negligence or fracking-related accidents can have devastating effects. Fracturing directly into underground water, hazardous underground seepage and leakage, and inadequate treatment and disposal of highly toxic wastewater can potentially contaminate drinking water around a fracking site. There's also concern about the threat of earthquakes and damaged infrastructure from pressure and wastewater injection. Links between fracking and increased seismic activity leave unresolved questions about long-term pressure imbalances that might be happening deep beneath our feet. Fracking's biggest controversy, though, is happening above the ground. The general consensus is that burning natural gas is better for the environment than burning coal, since the gas collected from fracking emits only half the carbon dioxide as coal per unit of energy. The pollution caused by the fracking itself, though, isn't negligible. Methane that leaks out during the drilling and pumping process is many times more potent than carbon dioxide as a greenhouse gas. Some scientists argue that methane eventually dissipates, so has a relatively low long-term impact. But a greater question hangs in the air. Does fracking take time, money, and research away from the development of cleaner, renewable energy sources? Natural gas is non-renewable, and the short-run economic interests supporting fracking may fall short in the face of global climate change. Experts are still examining fracking's overarching effects. Although modern fracking has been around since the 1940s, it's boomed in the last few decades as other sources of natural gas decrease, the costs of non-renewable energies rise, and cutting-edge technologies make it so accessible. But many countries and regions have already banned fracking in response to environmental concerns. It's undeniable that fracking has reshaped the energy landscape around the world. But for what long-term benefit, and at what cost?
So fossil fuels are a non-renewable resource, and whenever we're trying to think of renewable or non-renewable, we want to talk about can we make it again in our lifetime. So wood, trees are renewable because you can grow a tree within your lifetime, but fossil fuels take 300 million years to make. So yes, there eventually would be more fossil fuels, but you can't make it in a human lifetime. So this means that once oil, coal, and natural gas are consumed, they will not be replaced. And this shows a chart of million of barrels per day of fossil fuels that we pump out of the ground. And North America has been pretty consistent, but you can see these other countries are increasing quite a bit, and this only ends at 2002, so it's even more now. So many scientists believe that over half the world's petroleum supplies have been used up, but it's really difficult to tell how much oil and gas are left because the studies usually have a lot of bias in them. They're usually done by the oil and gas companies themselves, and of course they're going to say that, yeah, there's lots of oil and gas left, so that's a problem. And it's also under the ocean, it's in the ground. We don't know where all of it is, so that makes it really difficult to figure out how much we have left. So interconnectedness is central core to First Nations, Inuit, and Métis worldviews. So everything, including the people, the land, the lakes, the rivers, so living, biotic, and non-living, abiotic things are all connected. So this video shows how living things can affect non-living things in the earth really well.
One of the most exciting scientific findings of the past half-century has been the discovery of widespread trophic cascades. A trophic cascade is an ecological process which starts at the top of the food chain and tumbles all the way down to the bottom. And the classic example is what happened in the Yellowstone National Park in the United States when wolves were reintroduced in 1995. Now, we all know that wolves kill various species of animals, but perhaps we're slightly less aware that they give life to many others. Before the wolves turned up, they'd been absent for 70 years, that the numbers of deer, because there was nothing to hunt them, had built up in the Yellowstone Park, and despite efforts by humans to control them, they'd managed to reduce much of the vegetation there to almost nothing. They'd just grazed it away. But as soon as the wolves arrived, even though they were few in number, they started to have the most remarkable effects. First, of course, they killed some of the deer, but that wasn't the major thing. Much more significantly, they radically changed the behavior of the deer. The deer started avoiding certain parts of the park, the places where they could be trapped most easily, particularly the valleys and the gorges. And immediately those places started to regenerate. In some areas, the height of the trees quintupled in just 6 years. Bare valley sides quickly became forests of aspen and willow and cottonwood. And as soon as that happened, the birds started moving in. The number of songbirds and migratory birds started to increase greatly. The number of beavers started to increase because beavers like to eat the trees. And beavers, like wolves, are ecosystem engineers. They create niches for other species. And the dams they built in the rivers provided habitats for otters and muskrats and ducks and fish and reptiles and amphibians. The wolves killed coyotes, and as a result of that, the number of rabbits and mice began to rise, which meant more hawks, more weasels, more foxes, more badgers. Ravens and bald eagles came down to feed on the carrion that the wolves had left. Bears fed on it too, and their population began to rise as well, partly also because there were more berries growing on the regenerating shrubs. And the bears reinforced the impact of the wolves by killing some of the calves of the deer. But here's where it gets really interesting. The wolves changed the behavior of the rivers. They began to meander less. There was less erosion, the channels narrowed, more pools formed, more riffle sections, all of which were great for wildlife habitats, the rivers changed in response to the wolves. And the reason was that the regenerating forests stabilized the banks so that they collapsed less often, so that the rivers became more fixed in their course. Similarly, by driving the deer out of some places and the vegetation recovering on the valley sides, there was less soil erosion because the vegetation stabilized that as well. So the wolves, small in number, transformed not just the ecosystem of the Yellowstone National Park, this huge area of land, but also its physical geography.
Okay, so that's it. I will post an assignment, and thanks for watching.